let's start today's journey, right? So it's a division 1 problem and its rating is 2200, so it's quite hard. It's posted by Smile. So thank you, Smile. And we are going to explain this problem by introducing the example here, right? So in the example, the first number is the number of nodes in a tree, right? We have 3 nodes, right? And the second array indicates the parent of each node, right? So node 0 always the root, so it doesn't have a parent, so it's not showing in the second array. And so for the node 1, its parent is node 0, so we give them an edge. And node 2's parent is also 0, so we draw an edge here as well. So for the third array, it shows us the color of each node, right? So for color 0, it doesn't, it's white. And for the node 1 is black, right? We color it. And for the node 2, it's black as well, so we color it. So this is our tree here. So what's output? So the output is the number of possibilities of valid subgraph. So what's a valid subgraph? So a subgraph is a graph that same as this one, but we remove a certain number of edges, right? So let's say we remove this edge so that we got a graph like this, right? And for this graph, we can see that each of the connected components has and only has one black node. You see, this connected component has exactly one black node, and this connected component has and only has exactly one black node. So this subgraph is a valid subgraph, right? And we can find out another valid subgraph, which is like this, right? So we keep this edge, but remove this one, so that we got a subgraph like this. So it's also a valid subgraph, right? So this connected component has one black node, and this connected component has exactly one node, right? And can we find more? So let's try. We can keep both of the edges here, like this guy. But this connected component has two black nodes, so it doesn't satisfy the condition, so it's not valid. And let's try to remove both of the edges. So we got it like this, right? Is it valid? No, because this connected component doesn't have any black node, so it's not valid, right? So in total, we got two valid subgraphs, so we output 2. So it's a problem to count the number of possibilities. So for this kind of problem, we usually use dynamical programming, right? And this is a tree problem, so we use dynamical programming in a tree fashion, right? And for dynamic programming problem, the most important part is to find out the definition of states, right? So let's discuss the definition of states here, right? So we are going to calculate fp0 for each node, right? P is the number of the node, right? 0 means P is not connected with black, right? So let's say P is this node, and this node is black. So this kind of subgraph can be counted in the fp0, right? So if fp0 equals to 2, that means we have two subgraph like this, right? So let's say we got one like this, and we got one um, like this, right? Two in total, two. So what's P1 here? So instead of P not connected with black, this guy is connected with black, right? So I guess I made a mistake before. So actually, these two subgraphs are counted in this value, but because the P here did connect with the black, right? This P connect with the black, and this P itself is the black, right? And for this kind of subgraphs, it will be like this, right? Right? These two subgraphs, P doesn't connect to any black nodes, so they are counted in this value, right? Because P is not connected with black, right? So let's say if we got a tree like this, we are going to calculate F0 and F1 for each node, right? And we are going to do this in a bottom to top way. So we first calculate the bottom layer of this tree, right? We calculated these two guys. We calculated the 0 and 1, 0 and 1, and after calculate all these nodes children, we are going to calculate this node itself, and the calculation is based on the value of these four numbers, right? And after we calculate this node and this node, we can calculate the root node, right? And the root node's value is calculated based on these two nodes, right? So we are doing this in a bottom to top way. So what is exactly the way we calculate those numbers? So the algorithm is here, right? It's very simple. So let's say the node P is a black node, right? This guy is a black node. And we already know, we already calculate all its children's value, right? This is C1, children 1, C2, C3. So if P is black, and then fp0 equals to 0, because if it is black, um, P cannot be not connected with black, right? It always connected with black because itself is black. So the number of possibilities is 0, right? So what's fp1 here? So it means P is connected with black. So let's see how to calculate this value here, right? Because P is black, so if C1 is white, uh, if we choose C1, if we choose this possibility, we choose this state, then it means C1 is not connected with any black node, right? Because this guy is 0, so C1 is not connected with any black node. So it has to connect with P, right? Otherwise, this subgraph won't has a black node. So this guy must connect to the node P. And what about SC2 1 here? So if we uh, choose SC21 here, it means C2 is connected with the black node. So it has to remove the edge, right? If if it connected with the node P, then this subgraph will have two black nodes. That's not what we want, right? Because it already connected with a black node. It cannot connect to another black node anymore. So in either case, the edge is already decided, right? Whether we choose to keep the edge or remove the edge is based on what kind of state we choose for the node, for the children node, right? So we can just add the number of possibilities of the children node together, and we multiply to all of the children's, right? So what's the number of possibilities for this children? There are, let's say, uh, 8 possibilities. Then and this guy has 2 possibilities. This guy has 3 possibilities. We just need to multiply them together, right? And that's the case when P is black, right? It's quite easy here. So what if P is white? So let's say P is white here. So first we calculate the FP0, right? So this guy is not connected to any black, right? So if these children, we choose FC10, right? Which means it doesn't connected with any white as well. So these two guys has to connected with each other, because if this C1 doesn't connect with P, then it has no um, it has no possibility that it can connect with another black, right? We connect this node with P because P might connect to its parent, and its parent might connect to other black nodes, right? So we have to connect these two white nodes together. And what if a child we are a child already connected with the white with the black, then we want connected with P, right? Because if we connect this node with P, then P will be connected with the black node. That's not the definition, right? So in this way, when we decide the number of possibilities for each children, we already decided whether we are going to keep or remove the edges here. So as we did before, we can just add the possibilities together for each node, then multiply all of the nodes together. Then we got the total possibility of this node, right? And for FP1 is a little bit more complicated. So let's say we have P got a 3 child node. So FP1 means P is connected with the black, right? So let's say we got multiple nodes got connected with black. We can only choose one, right? We need to choose one and only choose one. So we choose for the first case we choose C1 to connect it with a black node, right? And then for the rest, if this guy connected with a black node, then we remove the edge between them, right? Because we can't let the P connected with two black nodes, right? So if this node is connected with the black node, we need to remove the edge. And if this node doesn't connect it with any node, then we need to keep the edge, right? Because we have to make sure this node is going to connect it with black node, right? So that's why we are going to calculate the total possibility for the rest of the nodes, right? And multiply them together just as we did before. But we need to exclude the node we are chosen for the black node, right? We need to do this for each black node, right? For each child. So this part is where we choose this guy as a black node. And this part is where we choose the second guy as a black node, right? And we are going to do this for each node, for each children node, and we are going to add them together, right, to get the final value of the node P possibilities, right? So I guess that's it. That's the way we calculate the possibilities for each node. Let's see the code here. So this part is where we read all the edges, right? We we are going to keep the edges as the children, right? So let's say we got a 0, 1, 2, 3. We are going to save all these three edges into the array 0, right? So when we travel to 0, we are going to easily travel to all its children nodes, right? And this part is just read the colors of all the nodes. Oh, sorry about that. Um, and we are going to start from the root node, and we are going to recursively travel to its children node. And when we track back, we are going to do all the calculation. That is how we solve the problem from bottom to top, right? First, we do a deep first search and get to the bottom of the tree, and then we calculate and track back, calculate and track back, and calculate the node until all of the children nodes are calculated and tracked back, right? Uh, here is the recursive part, and here is the uh, track back part, right? When we calculate all its children, we are going to calculate the possibilities of the node itself, right? First, we are going to calculate the sum of all the possibilities of their children, right? So we are going to multiply the possibilities together and store the data in S, right? We are going to use the S in multiple times, right? And here is the part where the node is black, right? So in the algorithm, if the node is black, then its fp0 is 0. If fp1 equals to s, these are easy. So this is the tricky part, right? So in our algorithm, let's take another look at our algorithm. So in the algorithm, we are going to calculate this guy, right? Essentially, this guy is this guy, which is S, divided by um, this guy, right? So we already calculated the multiplication of all these children nodes, and we just need to exclude one of it, right? So we divide S by fc1 0 plus fc1 1, right? In this way, we can easily get this value, right? So in the code, this part, sorry, in the code, this part is essentially the same as S divided by C0 plus FC1. So if the number is small, right, we don't have a mode, this guy is essentially equal to this guy. But because we have mode here, it's a little bit more difficult. So let's say um, let's say um, if we know C, we can calculate, we know C and B, we can easily calculate A by divide C with B, right? So we get A. But when we, uh, but when our A multiplied by B is modded by M, and we get a C. If we know C, M, and B, how we get A? We're going to use modular division, right? So this part is where we use modular division. So it's like a bunch of code you can just copy paste and just use it. I actually don't know the implementation. So if you are interested, you can find the implementation here, right? This ex explanation is quite good. So if you are interested, if you are just like me, doesn't care about the implementation, you can just copy paste the code and just use it here, right? It's not a big deal. So and you are after you get the other part, you are going to multiply it by using FC1 and add it into the final answer. And in the end, you are going to output it. So I guess that's it. So here is the code, right? So this big part is the part where we do modular division. So it is the exact code copy from here, right? So you can copy my code as well. So good luck. Thank you for watching.